The fore and aft position of the centre of gravity will have a significant effect on longitudinal static stability. The illustration shows a centre of gravity position at which the stabilizing tail moment is bigger than the destabilizing wing moment. The aircraft will have some measure of longitudinal static stability. If the centre of gravity moves forward, the length of both arms change. The tail arm becomes longer, which makes the stabilizing moment bigger. And at the same time, the wing arm becomes shorter, which makes the destabilizing moment smaller. Therefore, with the centre of gravity in a more forward position, the aircraft has more longitudinal static stability. If the centre of gravity moves aft, the length of both arms will change again. The tail arm becomes shorter, which makes the stabilizing moment smaller. And at the same time, the wing arm becomes longer, which makes the destabilizing moment bigger. Therefore, with the centre of gravity in a more aft position, the aircraft has less longitudinal static stability. Now let's consider what would happen if the centre of gravity is moved further aft. A CG position would eventually be reached when both the destabilizing moment and the stabilizing moment are the same. If a gust were to change the angle of attack, the aircraft would be displaced from equilibrium, but no net pitching moment would be generated. The aircraft would not displace any further, but would not start to return towards its previous equilibrium either. It would stay displaced. What type of longitudinal static stability would this be? Neutral longitudinal static stability. The CG position that will give the aircraft neutral longitudinal static stability is called the neutral point. Operationally, you would never fly an aircraft with the CG on the neutral point. You might think that neutral longitudinal static stability is not too bad. But remember, the aircraft must always be flown with a margin of safety. If the CG were to move after the neutral point, the aircraft would have negative longitudinal static stability, and when hit by a gust, will continue to displace from equilibrium, which is obviously not acceptable. Having returned the CG to the neutral point, we will now consider the acceptable CG range. If we move the CG slightly forward of the neutral point, the aircraft would have a small amount of longitudinal static stability, but there would still be an insufficient margin of safety. Moving the CG slightly further forward will increase longitudinal static stability a little more, but will still not provide a big enough margin of safety. With further forward movement, eventually a CG position will be reached when the minimum acceptable longitudinal static stability exists. The CG position that guarantees minimum acceptable longitudinal static stability is known as the aft CG limit. Operationally, the CG must never move outside the aft CG limit at any time during the flight. Calculating the CG position during the entire flight will be fully covered in a different subject called mass and balance. If we now move the CG forwards of the aft CG limit, the longitudinal static stability will increase. But we don't want the CG too far forward, because there is such a thing as too much longitudinal static stability. You might think the more longitudinal static stability, the better. But no. In addition to our example gust, the pilot can also momentarily change the angle of attack when a pitch input is made. Longitudinal static stability will oppose the pilot's pitch input in the same way it opposes a gust. The greater the stability, the more the resistance to pitch input. So, in addition to the effect of CG position on longitudinal static stability, we must also consider the effect of CG position on the ability of the pilot to maneuver the aircraft in pitch and the stick forces required. Consequently, to ensure minimum ability for the pilot to maneuver the aircraft in pitch, plus ensure the stick forces are not too high, a forward CG limit is required. The forward CG limit will give maximum longitudinal static stability and guarantees minimum acceptable maneuverability and maximum acceptable stick forces. The aft CG limit will give minimum acceptable longitudinal static stability and gives maximum maneuverability and minimum acceptable stick forces. We will now take what we have learned about longitudinal static stability and, using simple sketch graphs, consider some of the variables. Here are the two axes. The vertical axis represents pitching moment, with increasing nose-up pitching moment above the horizontal axis and increasing nose-down pitching moment below. The horizontal axis represents lift coefficient, increasing to the right. Your previous knowledge will tell you that the horizontal axis could instead be labelled angle of attack or decreasing indicated airspeed. As you will see, all three values need to be considered to give a full understanding of these graphs. For the time being, we will use lift coefficient for the horizontal axis, but you need to keep the two alternative values in mind. An aeroplane in equilibrium is shown on the horizontal axis. How do we know it's in equilibrium? Because it is not generating a nose-up pitching moment or a nose-down pitching moment. An upward acting gust has increased the lift coefficient. And because the aircraft has some longitudinal static stability, it will generate a nose-down pitching moment. The nose-down pitching moment will start the aircraft back towards equilibrium. Remember, longitudinal static stability is just the initial reaction to a change in angle of attack. The graph is reset with the aircraft in equilibrium. A downward acting gust now decreases the lift coefficient. Because of its longitudinal static stability, the aircraft will once again generate a pitching moment, but this time it's a nose-up pitching moment. The nose-up pitching moment will start the aircraft back towards equilibrium. The graph is again reset with the aircraft in equilibrium. If we join together the point on the graph that represents the aircraft in equilibrium, the point that represents the pitching moment generated by an increase in angle of attack, and the point that represents the pitching moment generated by a decrease in angle of attack, the plot will represent a longitudinally statically stable aircraft. The curve on the right-hand end of the plot shows the aircraft nose-down pitching moment at the stall. Now let's use the graph to consider variations in longitudinal static stability. Movement of the red dot shows an increase in angle of attack, which generates a nose-down pitching moment. Reset the graph to equilibrium. A decrease in angle of attack generates a nose-up pitching moment. Now we'll look at a decreased level of longitudinal static stability. The same increase in angle of attack has generated a smaller nose-down pitching moment. Reset the graph to equilibrium. The same decrease in angle of attack has also generated a smaller pitching moment, but this time nose up. Now we'll look at an increased level of longitudinal static stability. The same increase in angle of attack has generated a much bigger nose-down pitching moment. Reset the graph to equilibrium. The same decrease in angle of attack has also generated a much bigger pitching moment, but this time nose up. The green plot shows longitudinal static stability. The blue plot shows less longitudinal static stability. The magenta plot shows more longitudinal static stability. The direction of all three plots is downward, from left to right. This indicates positive longitudinal static stability. The angles of the plots shows the amount of longitudinal static stability. The steeper the plot, the greater the stability. What does this plot represent? An increase in angle of attack generates no pitching moment, nor does a decrease in angle of attack. This plot represents neutral longitudinal static stability. What do you make of this plot? An increase in angle of attack generates a nose-up pitching moment. This is not good. Reset the graph. A decrease in angle of attack generates a nose-down pitching moment. Again, this is not good. When the slope of the plot is upwards, from left to right, it represents negative longitudinal static stability. As with positive longitudinal static stability, the steeper the slope, the greater the instability. Here are the three types of plot we'll be using from now on: stable, neutral, and unstable. So what does this plot represent? Here's a big clue. The plot represents an aircraft with a swept wing. Stable at high speed, because the plot slopes downward to the right. The plot continues to slope downward to the right as speed is reduced. But the slope is becoming less steep, which represents a slight decrease in longitudinal static stability. With further reduction in indicated airspeed, the stability becomes neutral. From your previous studies of swept wing stall at higher angles of attack, tip stall will begin. And like all swept wing aircraft, this will generate a nose-up pitching moment. In the next segment, we will be using graphs like these to illustrate other variables.